This is Team 70. Our project is multi-aspect sentiment analysis and recommender systems. The motivation of our project is try to utilize users' review text in building recommender systems. Current recommender system relies on user feedback, which typically consists of a review and a numeric rating. The feedback is used to train the model-based collaborative filtering algorithm, which predicts the ratings that the user will give to items that they have not reviewed. However, the other part of the feedback review text is ignored by the current recommender systems. In our minds, review text justifies the ratings and contains more information about user preference as well as the properties of the item. Ignoring this great source of information is a big shortcoming of current recommender system. For example, if a user has just several ratings among thousands of items, it's very hard to model the preference of this user accurately. The current system might find a parameter vector that fits a data sample very well, but actually reveals too little information to be useful in practice. This is usually called the cold start problem. We want to tackle with the cold start problem by interpreting the information contained in the review text, and we believe it will strongly support the current recommender system and brings improvements in prediction accuracy. Here's an overview of our project. We define 4 aspect categories for restaurant reviews: food, service, ambience, and price. In our project, the words item and restaurant are interchangeable since we only use restaurant review text. And the words aspect and aspect category are also interchangeable in this project. And we called the extract information feature vector. A feature vector for user is computed based on all reviews the user ever gave to all items. On the other hand, a feature vector for item is computed based on the reviews that the item got from all users. We calculate the feature vector using sentiment analysis. The detailed information will be discussed later. We integrate the pre-compute feature vectors to the objective function of the traditional collaborative filtering model. In this way, we combine the latent rating parameter vector with a review text feature vector. We call our model as Word Embedding Collaborative Filtering, or WECF for short. We implemented the WECF model in Python and trained it with parallel stochastic gradient descent. After 5-fold cross-validation, the WECF model does demonstrate better performance in terms of mean square error than traditional collaborative filtering model. We basically develop our own algorithms in Python, and we use several libraries such as Word2Vector, TextBlob, and Spark. Word2Vector is try to determine the aspect of the sentence. TextBlob is used to do sentiment analysis, and Spark is for MapReduce. And here are our assumptions and intuitions. So to compute the feature vector, we have 2 important assumptions. First, a user will discuss the item properties that he or she most cares in his or her reviews. For example, a user usually mentions service of a restaurant, while seldom mentions the food in his or her reviews. Then this user probably values service of a restaurant much more important than the foods, and therefore we need to recommend a restaurant with excellent service to this user. So each element of the feature vector computed from one review of a user represents the extent the user's attention to each property of the restaurant as the number range from 0 to 1 in this review. Second, an item's properties will be heavily discussed in the reviews about pros and cons. For example, two restaurants might have same average ratings but different strengths and drawbacks. From the real test of the first restaurant, we can infer which exact property that the restaurant is good at or not good at. We can do the same analysis for second restaurant, too. So each element of the feature vector computed from one review of a restaurant represents how this restaurant behaves on each property as a as a number ranges from -1 to 1 in this review. We denote user's feature vector as u hat subscript I and the restaurant feature vector as v hat subscript j. The detailed calculation method and how we will use the feature vector will be introduced in the later slides. And now let's look at the inner product of two vectors. So if we want the inner product of two vectors to be large, then we need the items we want the same position have. Let me refuse. So if we want the inner product of two vectors to be large, then we need the items in the same position to be positive and as large as possible. So let's say AX represents the food, how a restaurant behaves on food, and BX represents how a user cares about food. If AX is large but BX is 0, then it doesn't matter. So the user doesn't care about the restaurant food, no matter how good the restaurant behaves on food, that just doesn't matter. So we want the inner product of users, the user, and we want to match the restaurant properties and the users, how user cares about these properties. And to do that, we want the inner product of these two vectors be large as possible. And here is the objective function of our mode embedding collaborative filtering model. So compared to traditional object function of collaborative filtering model, we have these two items in the red square, these two items, additional items. To minimize these two items is equal to maximize the two inner product of these two items. The first inner product is the feature vector of user I times the parameter vector of item j. Since the feature vector of user I is pre-computed from user's review text and thus is treated as constant in our objective function. To maximize the inner product, we want to encourage the latent parameter vector of item j to have positive element at the positions where feature vector of user I have non-zero values. This can be interpreted as we try to fit the latent parameter vector of item j follows user's preference. Similarly, the second item, the second inner product is a feature vector of item j times the parameter vector of user I. We treated the feature vector of item j as constant here. To maximize the inner product, we want to encourage the latent parameter vector of user I to have positive element at the positions where feature vector of item j also have positive elements. This can be interpreted that we try to fit the latent parameter vector of user I with the consideration of how the item behave on each aspect. We implement this model in Python. And here is a system pipeline of our project. So we first do some data pre-processing of the raw data. We extract all the review text and feed the review text to the word-to-vector encoder. And we train word-to-vector model based on the entire review text. Then we group the review text by user and by item respectively. And we use the word-to-vector to find the aspect of each item of each sentence. Then we do sentiment analysis to compute the feature vector for users and restaurants. By feeding the feature vectors and the ratings data to our word embedding CF model, we can optimize parameter vectors for user and restaurant by stochastic gradient descent. And the parameter vectors just our recommended system, and we can predict the ratings for of a user and item. So we can implement the original stochastic gradient descent in sequential way, but for a large data set, this is computational expensive. So we want to use Spark to accelerate this process. We want to use Spark to do parallel computing. So we first divide the whole matrix into several blocks as shown in this figure. The user's axis and the restaurant axis are both to be divided into n segments. So the whole matrix is divided into n squared blocks. And the number of n here is set by cores we have. So we have 4 cores, so we will divide the matrix by these 4 blocks. In every iteration, we do computing on n blocks parallel. So first iteration will do these 4 blocks at the same time. The method is to update the blocks in diagonal order. We want to do this first, and this, and the third. In this way, each block will not affect each other. So, in other words, we can compute all blocks that are in the same diagonal parallelly. The data set we use is restaurant review test from the 8th round YAP dataset challenge. It contains 2.7 million reviews and 649,000 tips by 687,000 users for 86,000 businesses. There are many challenges in our project. Implement the word embedding collaborative filtering is much more harder than implement a traditional recommender system. We don't have an existing solution. We have to code our own. We have to code our own algorithm. And before that, we did a lot of researches, and we try to come up a rhythm model, and we implement in pure Python. Then we train our model with stochastic gradient descent, which is very time consuming. So we try to use Spark to implement a distributed way that we can utilize the MapReduce property of Spark and to try to accelerate this process. Using word-to-vector, we determine 4 aspect categories: food, service, ambience, and price. And we define the representative words for these aspect categories as food, service, ambience, and pricey. And this figure shows the grouped words for the aspect categories respectively. It shows the word-to-vector model does work, and it can give us the aspect of each sentence respectively. And here is an example of how we do multi-aspect sentiment analysis. As shown in this figure, the review has 4 sentences. The sentence in green is about food, and the sentence in blue is about service. Both colored sentences have positive sentiment, and this review does not mention ambience and price. The other 2 sentences has no aspect involved. Apply the algorithm for calculating user and review feature vector, we can get the following feature vectors. Assuming the number of dimensions is 5 and the sentiment analysis output 0.5 and 0.45 for these 2 sentences. So the way we compute the user feature vector is there's one sentence mention food, and there are 4 sentences in the entire review. So we do 1 divided by 4, which is 0.25. Similarly, 1 sentence mentions service, and there are 4 sentences total. So 1 divided by 4 is 0.25. That's for service. And we do sentiment analysis on the sentence on food, and the library output 0.5 as the polarity score, and we just use it 0.5 as the value of our feature vector. Okay, and after building our prototype, we did experiment and to evaluate our model. We have the hyperparameter set as the following. So the dimension equal to 5, the step size of and the iteration time we define as 0.001 and the 100 iteration for stochastic gradient descent. We set the for 1 and for 2 to 0, not include the regularization term, just for the simplicity, and we just have 1 as constant for our new terms. So we try to measure the mean squared error for both collaborative filtering model and our word embedding collaborative filtering model. And it turns out our model has 4.3 improvements on the training errors and 1.6% on the cross-validation error. In this figure, we show the mean squared error decrease as the iteration time increase. So for each iteration, we go through the entire data set and do stochastic gradient descent. After 100 iteration, there's still a room to be improved, but due to the it's very computational expensive, we just stop at 100 iteration time. To conclusion, by extracting review information through multi-aspect sentiment analysis, we analyze the user preference and the restaurant characteristics. We have present word embedding collaborative filtering model. It combines the ratings with review tests for item recommendation. The WECF model works allowing users and items latent parameter vectors in ratings with their feature vectors in review text. The model can accurately fit user and item parameters by only a few feedbacks. We evaluate WECF model on YAP round 8 dataset consistent of 2.7 million reviews and 649,000 tips by 687,000 users for 86,000 business. We have shown that WECF has better performance than traditional model-based collaborative filtering approach. So, some feature work. First, we want to add offset parameter and the users and the restaurant buyers parameters to the object function of our prototype. Previously, for simplicity, we omitted these parameters. And we will do more validation and testing to further prove that the model does work better than state of the art. In addition, we would like to explore the possibilities of using WECF model to facilitate other natural language processing tasks on review text, such as representative reviews identification and review gene discovery. Moreover, we want to modify the current algorithm to compute feature vectors based on every aspect direct instead of grouping them into predefined categories. In this way, we can generalize the idea to general items instead of just restaurants in our project currently. And thank you for your time. Thank you for watching, and Have a good day.